Login accepted.
Good morning. I hope, seems like the audio works, and very impressive intro there. Just before I start going into this topic, there has been a room change this morning. So if anyone in here is here for load balancing or load testing, I think a talk from Renee, this has been moved to room 4B, and mine has been taken over here. But I think most people can see it from here. This one is about container builds, I think my room got upgraded before because a lot of you put a star into the mobile app. So thanks very much for your confidence there. I hope I'm not going to disappoint with this talk then. Thanks for being here early in the morning. I know this is, and when you're on conferences, this can be a bit difficult sometimes. Now, let's go into the topic. Or before I start, maybe a quick introduction about myself. My name is Matthias. I am from Germany. I work for a company called Novatech, and basically what I'm doing there is trying to help people in terms of cloud-native software engineering. So I have a bit of a side on implementing code and the programming side, but also the platforms and DevOps kind of thing. And this talk is kind of where it right meets in the middle about how to package your applications in containers. So next to my job there, I also try to help people externally, in particular students. So I'm teaching distributed systems and modern software architecture in 2 universities in the area of Stuttgart. So this also helps building up those things for the talks. All right. So in a very simple way, what this talk will be about, coming from having Java code and going towards having that in a container image. So there's still people joining. Maybe I'll wait a few more seconds, as we haven't fully started yet. So it's slowing down now. All right, and I guess most of you have done that in one or the other way. And this is what we're going to talk about, the one or the other ways. So talking about containers, people talk, of course, about Docker a lot. This is what made containers very popular, and one of the things that made it popular is the thing called Dockerfiles. So we're going to look a bit and what are the various options of how to use those Dockerfiles. And then we'll see there are also a couple of other options how to bring your code into containers. Now, I'm not able to cover all of them within 45 minutes, but I'm certainly trying to cover a few. And then in the end, try to figure out, okay, what can we learn from all that? What could be a good strategy for you in your current situations on how to build good and robust images. I have an underlying kind of walkthrough. I'm demoing quite a few steps live, and there is an underlying kind of lab. This is in a public Git repo, so there's a QR code here. I'm going to show it again at the end, so you can still decide then if you like the talk or not, and access the repo. Then it's going to still be there. So you will see it throughout the talk. Okay, so to start very simple, it's early in the morning. Let's say, okay, go back to what a container actually is, because understanding the fundamentals of a container will also help us to understand how can I make the image process better. So in the end, what a container is about is to have an isolated process or application that kind of brings in all necessary process libraries and dependencies. Under the hood, a container is being isolated within an operating system using things like namespaces, change root, and C groups. Normally, people don't really interact with that. They interact with a container daemon like Docker that kind of abstracts all that low-level stuff away. But on top of that, there is still that container thing, which the name says contains all the things that are necessary. So a container image what we're kind of looking at today is that template that basically can be taken by a container daemon and then turned into a running container. The way those container images are being built up is in the form of layers. A container image, most of you probably know that, is not the one big blob that lies in the file system. So it's separated into different layers, and that gives the container daemon the ability to reuse the layers across different images. Even if the image content or like the full content might be different, there might be still some overlapping pieces, and handling them efficiently will also improve like your container game. So this, in a very simple way, is how things could be built up for a Java environment. So you have a base image with Ubuntu, then you have a layer with the Java runtime, and then you have a layer with the application on top. In the very beginning, the only way to actually do that was to like run a certain image or like execute a run command on an image. Then you get a container, you put something into a container, you do a commit generates the next layer, and you have a new image and do that again. Fortunately for all of us, this didn't stay very long. So I think Docker came out in 2013 in March. And if you look into the Git history in May, was the first time the thing called a Dockerfile was mentioned. So most people have never really used Docker without a Dockerfile. Same for me. I did this research, of course, later. Now, these Dockerfiles are probably over 90% of how people build container images. Also, if you go like on the Docker Hub, you find documentations. This is, for example, documentation if you want to go for the latest Eclipse Tamarind image. Then they would say, okay, these are 4 lines of Dockerfile, which do exactly the same thing as I had shown here. So it takes a base image, it creates a folder, copies your application inside, and then does the container command. So every time you invoke a run, it will call Java and run your jar. Now, this is the thing I try to challenge today, because I think that could be and can be done better. And we will see how things go. So, yeah, as I just said, those Dockerfiles, they operate kind of in a batch mode. So you basically have your first line that will normally pull in your base image. Then you do a couple of set of commands. And each line of these Dockerfiles will generate a new layer in the later on image. So you can, for example, in this way, I take a base Ubuntu, and then I install the JDK in such an image, copy in the jar file. This one also already brings a base image which has the JDK inside. And this is kind of the tricky thing. There are many. So you have a combination not only of Java versions and not only of Java distributions, but also of various base images. And some people might actually think about it and say, okay, which is the one to do it better or worse, and what could potentially happen. Now, the tricky thing with these Dockerfiles is they might deprecate. Or let's say like the base images might deprecate. That actually happened to me. And if you build a Dockerfile, you wouldn't get notified. So this adopt OpenJDK that I had in the very beginning, like 2 or 3 years ago, when I started doing this presentation in there, just kind of got taken out. I didn't know this in the first place, and I was still building the images with that. And Docker would not actually complain and say, be careful, you're using a deprecated image. There is no mechanism in there. So beware of that and check on your base images before you ever try to apply them. I mean, it would still stay a Docker official image and so on, but has this little deprecation notice. All right. So moving on in the evolution of those Dockerfiles, in 2017, Docker included a thing called multi-stage Dockerfiles. So just a quick question. Who has been using multi-stage Dockerfiles in here? Okay, so that's almost half of it. Yeah, it's been around for a bit. And just to recap real quick, what you can do with this multi-stage Dockerfile is, as the name says, separate your file in multiple stages. Multiple stages basically means multiple intermediate and one final image. So in here, we have seen like the part on top would actually serve as an image to build the code, and the one on the bottom would actually be one to run the code. This is, in my opinion, a lot better than the example that we have seen on that Tamarind side, because if you do it like this, if I go back here real quick, this still leaves it open completely. Where does this JApp jar actually come from? So you don't have that part covered or specified. That could be a harmful or not well-built thing, and it leaves still the possibility to build it in different environments, and there is no real check on that. So if you do it like this, then you can go sure that your builder image, in that case is a Maven Temurin 17 image, will always be the same one. And then you copy your code in and build the image always under the same conditions. So you have a higher degree of standardization, and you can ensure it will always be built with the same Java runtime, or like the same Java version, under the same conditions. And the portability also increases to do it in different environments. And then on the part on the bottom, you basically take the jar file. So the part on the bottom is actually very similar to what we've seen before, except that copy statement has this -from build part. This is the same build label that I gave above here. So it copies the jar file out of that intermediate image and puts it in there. So you will always get the same kind of settings if you use that. Now, this wasn't the end of the Docker evolution there. In 2018, it was still in beta. They announced that BuildKit environment, which is basically the standard now. And this also tried to optimize the images. So it would claim to have smaller images, better caching, flow logic, security, and so on. So with that, it's now possible to, if you have multi-stages, you can build the stages in parallel. That will improve your speed. You can build flow logic in there, but in turn, it also gives you the possibility to make your Docker file way more difficult to understand. So not everything in there might be a help or might be actually needed. So this is something that you have to decide for yourself. So this is more like pseudocode. So those things wouldn't run, but I just kind of compressed a little bit to make the slide more readable. All right. So one of the things that this part, however, introduced was the option to cache. I mean, caching things is basically possible if you run container images, but it was not possible until then with in the build step. So if you run an image like this for the first time, or basically for every time, it will always be in a fresh container. So it doesn't know it has been run on that host environment before. And if you invoke a Maven command there, it will, of course, download the entire internet and then repeat it over and over again. So that makes it consistent, but it also makes it take a while. So if you use that cache, it allocates a directory outside of the container that it can go back to. Of course, this makes it more vulnerable, so you have to decide for yourself, but at least the option is there. So I would recommend, of course, to use that in development cycles. Later on, if you build for production, you can, of course, skip it then and do a clean build. All right. So from all that, what can we kind of derive? What makes a container image better or worse than another one? We have seen, build speed, size, structure, standardization, security topics, and so on. Potentially also the JVM configuration. This is something that I don't really cover in that talk, but all the settings for heap size and garbage collection, you can also specify. This is also something that wasn't given in that sample before. Yeah, and again, this is how it is given on that website, and I think we can do better than that. Now, a quick word about the size. So, as I said, the image consists of layers. You have a base layer, you have certain dependency layers of libraries and other things, and the application on top. Now, if you rebuild your application over and over again, most likely the top layer will change with every build, because then you get a new code artifact. But the layer on the bottom should actually change very, very rarely, especially on the base OS side. So many people try to optimize on the base OS layer and squeeze things out there, which in my opinion doesn't make a whole lot of sense, because this layer will be downloaded by the container daemon only once and then be cached. So it's more like that the things that change on the top can be optimized. Now, if we look at Java in particular, we have a similar structure there. So we have also class files on the very top. These are the things that probably change mostly. We have resource files, and we have the dependency jars. That shouldn't change with every code change. It's more like change when you add something to your POM XML or Gradle file and add some and remove some certain dependencies. So potentially, we can continue on that optimization, looking deeper into Java. And that works with this kind of extract mechanism to extract a jar into those 4 layers that you see here on top, where you have like, this is a Spring Boot example, where you basically have dependencies, Spring Boot loader, and then the application on the very bottom. So this is, and if you only do a minor code change, this would be the only thing that changes in your subsequent builds. So if you build very often, you only have kilobytes of a layer change, as opposed to a couple of megabytes, or I don't know how big your jar file would be. I mean, again, we're not talking about certain big magnitudes, but it certainly makes more sense than optimizing on your OS level, or like your OS base image, as this one has a more frequent change. All right, so as you can see here, if we start combining all those things, like multi-stage build tools, caching, extracting, and so on, the files get more complicated. So maybe I can show a couple of, well, I'm going to continue here real quick and then wrap it all up on the Dockerfile things. So this is something which has been around for a bit, but I only learned about it through a blog post from Brian Vermeer last year, that you can also optimize on the side of your Java runtime. So with the, I think it's around since JDK 9 or 11, to use that J-Link tooling to build a smaller JRE, which basically only covers the things you actually need. This is also something that you would find on that Docker Hub page from Xamarin. So this part right here, where you say run Java home bin J-Link, will basically take your base modules of your Java file, and then just output a Java runtime which actually contains the part that you need. And later on, it takes a base image. It's just a plain operating system image for, in this case, a Debian Buster Slim, and then copies the Java runtime into that. So this is like a stripped-down Java runtime and then a full-blown one. And in the end, you can copy your Java file in there. I mean, this is not completely optimized, so I'll try to do that here. So this is like the Git repo that I showed you before, and I show again later, where I have like all the various types of Docker files in there. So starting from a very simple one, only 3 lines with that Xamarin image, and then the one that I would call the ultimate image, which has already almost 40 lines of code. So obviously, this one is more complex to maintain, but it will definitely have a better effect for your later on and repetitive build times. So just to walk through it real quick, it will copy the code in, then build the jar file, then basically get the dependencies out of that jar file, run J-Link with that dependencies, and so you get a fully customized JRE just for your initial build. Then in the next part, you extract the things, and then you build the final image, and then use that various layers of dependencies. So yeah, you see, there is a lot of possibilities. I mean, if you want, I can, of course, also run it. No, this is wrong. So where am I? Well, let's do it in a different way. Let's build a very simple one. And I'm going to use that Xamarin image there. So I say Docker build simple. I hope you can read that well, but you will see it in a second. So now, this will, So again, this one will totally rely on a jar that has been built before. So this is actually something that I have done before. Otherwise, it will not work. So if I look into Docker images now, sorry, I can't type. Let me make it a little smaller. I hope it's still visible. I'm a little bit limited with my screen size here. So this one will take 276 megabytes, and if I do like a Docker history on that image, it will basically reveal this is all the part that has been taken in from the base image. And then you can see here is that copy part, where I copy in 24.4 megabytes. This is actually my jar file, and specify that command. So that's basically my image structure. If you don't believe me, so if I do like an ls minus, so this is the 21.4 megabyte jar file in there. Now if I try to do optimize and that image and say, okay, docker build minus f Dockerfile, and now I'm taking this ultimate version. This will first of all have to pull different images. So if we look in there, it has that Tamarind image, it has that Ubuntu image, and it has that Maven image. This will actually happen in parallel, and now it's going to start that build within the container. So as it is doing it for the first time, even though we use cache, it doesn't have a cache yet. So it has to download all the dependencies, which it has done now. Now it's running that JDEPs and JLink step to basically build the JRE. And once this has been done, it will now copy all the various extracted layers into the final image. So if I look into that and say Docker images, we now have two. It is significantly smaller with 156 megabytes. And this is only that final image. So that intermediate images that have been built here, they are not being shown by Docker. So this is only the image that we see here is only the one from that step in the end. So if I do a Docker history there, and this is the 1, 2, 7. Now we can see, especially on the top here, we have a different entry point where I specified some parameters for the JVM. But also here, that 4 layers shows that from the 21.4 megabytes, 21.3 are actually dependency libraries. And only 6.51 kilobytes is application code. So when I do a rebuild of my application, only that layer will change, and all the other layers can be taken in from a cached version. So I can try that real quick and say I go into the application. This is just a sample CRUD thing, so I'm just going to modify the name of a method. Not a big code change, but still enough to actually have that rebuild. And I'm going to do that step again. And now the environment, first of all, we see, okay, there is a cache now, so it doesn't need to download the libraries again. So this step is significantly faster. This step will take the same time as before, but later on, the layers of the actual application code will also be taken in cached. And yeah, so you can see it here. All of them have been taken in cached. Only that final one of the application is coming in there as such. So if I do Docker images again and say Docker history, what is the ID now, 052, then I can see this is the only layer which actually has been exchanged. So with that, you can certainly speed up your builds, especially if you have kind of a repetitive environment there. Good. Is that all readable well? Okay. If I need to increase some font size or whatever, please let me know. I have screen limitations, but I certainly want to make sure you see it well enough. All right. So that was the part on the Docker files. And then this is probably where most people have stopped looking for alternatives, and I want to basically just show that there are a few more things. So this is like a sketch of a timeline of various container technologies that a friend of mine has done once. And if you look at it, there are, especially if you look at it time-wise, 2013 was the part when Docker was released. But there were already things before that, things called Buildpacks, which we're going to look into in a second. So technologies like platform-as-a-service technologies like Heroku or Cloud Foundry already had to deal with that thing to build a runnable artifact that you can execute on a cloud platform in a similar way as containers are being executed in Kubernetes nowadays. In 2014, Spotify came with a Maven plugin for Docker, so you could do a Maven build and also generate an image out of that. Then there was the OCI specification, which plays a certain role in building the images. A technology called JIB, that we're going to look into next, emerged in 2019. And then this idea of Buildpacks kind of gained new attraction by generating that CNCF project of Cloud-Native Buildpacks, which is in incubation state nowadays. Now, what does that all mean? We're going to look at JIB first. Just out of curiosity, who is aware of JIB in here? Okay. So maybe I can impress a few others. Now, if the thing with JIB is, as the J implies, this is can only be used for Java applications. I mean, the focus of this talk is kind of Java applications, but I want to go into a bit more breadth in the end and see, okay, how many of those things can you also apply if you have like a polyglot environment? So with JIB, I have mentioned that Docker plugin from Spotify before to generate an image out of the Maven build. This is in a similar way what JIB does. The interesting thing that you see here in that diagram is what you don't see, because you don't need a Docker daemon. So the image, as I said before, is under a certain specification. That is that OCI specification on how a container image looks like. So technically, you don't need a daemon to build that if you basically follow the rules. And that basically is what JIB does. So it can be used as a plugin for Maven and Gradle, and if you execute it, it will basically in the end come out with a jar file. It's very simple. And you have different ways to export it. So you can directly, for example, push it to the Docker Hub location. You can export it as a tar file. Or if you have a daemon running or you have a daemon present, you can also build it to your local daemon. The thing that I told before about separating an application into various layers on the Java side is something that JIB will do automatically. So this is not something you don't really have to do yourself. So in the end, you can cut down on many of those things we saw before by just executing one Maven or Gradle command. So I'm going to show that live real quick as well. So just have to look it up in my README. So this is a README where I do all the various, like I do way more steps in that README file that I have that I'm doing here in this talk. So if you want to replay everything for yourself, then you can certainly do that after that. So if I ever find it. So here is JIB. So you can, of course, add this to your POM file and make this thing happening automatically. You can also, however, invoke it just from command line. So I'm going to say clear so you can see that better. Okay, I don't have it in here in the history yet. So I'm just going to copy this one out. And we can look at the command real quick. So now this is better. So I'm doing a Maven compile, and then I specify that plugin right here. And at the end of the plugin, I specify Docker build. That means it will put the final image into the local image registry of my Docker daemon. So let's just try that real quick. So it's building the code now. this has, of course, as it's running for the first time, it has to download some of the dependencies. And then it's going to generate that image and is now done. So even with the dependencies, it has been working very fast. So let's say if we look at Docker images, we can now see here on the bottom, there is that Java JIB image. This one has a pretty similar size to the one that I have built in the first place. Now, if I look into the specs of that one and say Docker history FE8, no, F. We can see here on the on the top that JIB also does this breakdown of dependency, resources, and class files automatically. It also comes with like an own base image. But the thing, or like, let's say the thing to be aware of, is that the actual build of the Java code is now happening on my machine. So this is not like nested in a multi-stage container. So you have that this kind of build dependency on your local environment. If you, however, do this in a standardized like CI/CD pipeline, where the conditions are always the same, this shouldn't matter so much. Also, that limitation, that's just speaking of CI/CD pipelines, I've also seen companies that still use very traditional tools in there, like with build nodes that get just like over-installed again and again, and sometimes they have restrictions to not being able to run a container daemon there. Don't ask me why, but it happens. This is, of course, helpful here then if you don't have the dependency for such a daemon, and you just generate that container image out of that tooling. I could quickly show you how to push an image into a container registry. So, oh no, I can. I'm not going to do this now. Anyway, if I just look back into this command, I can at least try to do it. Here I have that Docker build option, and I think if I just specify build, it would not build to my local environment, it would try to push it. This will of course fail now because I'm not connected to any container registry. So it says, okay, it's not authorized to push it under that name, but that would normally go out and push the image to my registry. But you can see here it uses that Eclipse Tamarind 17 JRE image. That's probably because the code is still 17. So all of those things, you don't really have to worry about it. They come in with a standardized base image that you basically use for all your builds in there. And the only thing you have to do, instead of writing 40 lines of Dockerfile, is that single command. All right, I have only a few minutes left, so I'm going to hurry up a little bit. So Buildpacks. As I said, the idea of Buildpacks has been probably around longer than the idea of container, or at least the name of container. Heroku was initially the one who came up with the idea. So they had this public PaaS service and said, okay, please give us your code. We're going to take care of it and do all the rest. And the rest was basically the idea to have this underlying lifecycle to say, they're going to take the code, then they detect what kind of programming language is it. Is it Ruby? Is it Python? Is it Go or Java? And then they would build it and export it into some kind of runnable artifact. This is the same thing that we would call a container image today. This concept was adopted by Cloud Foundry, and both Heroku and Cloud Foundry continued the development for their own platform as a service solution. Now, somewhere in here between, in the timeline, there was suddenly that major disruption when Docker came to life and basically took the world by storm, and then even more popularity through Kubernetes, and everybody just wanted to have container images. And so the people in that from Buildpacks said, okay, we already have a mechanism to build those images in a standard way. So they created that Cloud-Native Buildpacks project, which is tries to create a standard, but it's open for various implementations. So there are implementations from Google, there are implementations from Heroku, and the implementation from the Cloud Foundry community flew into a project which is called Paketo. So this is the one that I'm going to look into now. And the way that works, you can see in a generic way on that image. So on that sketch right here. This one, if you execute it, certainly needs a Docker daemon to execute, because the first thing it does, it will download a very big so-called builder image. And I'm glad that I'm telling this now. I should probably download this before I demo that. So if I am back in here and say pack. So pack is the command. And the first thing I have to do is basically pick a builder. So if I say builder suggest, it would suggest me with some builders. And I would say, OK, I'm going to use this one called Paketo Buildpacks Builder Jammy Full, this one right here. It's based on Ubuntu 22.4, and these are all the things that it can do, like Go, Java, Java Native, .NET, Node.js, and so on. So once I specify that, I can now say pack build, and the first thing it's going to do, it's going to download that very, very big image. So let's give that a bit of time in the background, and we will come back to this. So it's going to download this builder image now, which doesn't only contain the build packs for Java, it basically contains all the build packs that I mentioned before. So in the end, my code will walk into that container of that image. It's going to be detected, and it will find out it's Java and it's Spring Boot, and then detect all the necessary build packs it needs to turn this into an image. And then it will create the image out of that, and also make a hopefully meaningful categorization into various layers. Now, why would you add something like this and create additional dependencies on the side of your image build? One of the important functionalities here is that so-called rebase functions. In the beginning of the talk, I told you that most often your images will change on the application layer side. Now I'll tell you something very different. Sometimes they might need a change on the base image side. And this is very often the case. I'm glad it's not so often the case, but this is often the case when certain vulnerabilities surface. So when something like shell shock, heartbleed, log4j, something like that emerges early in the news in the morning, what would people do? What is the first thing how people would react if some of those news come out and you like own a certain IT landscape? You would want to know, am I affected or not? And to find out if you're affected or not, you have to scan all your different environments and see what is kind of my stack in there, and is this library in there? Now, if you have consistency on your base images, and you have a vulnerability somewhere in an operating system level, you can very easily say, well, either all of them have it or none of them has it. And if all of them have it, they can quickly rebase all the images, and then you can go sure, and so operation can continue. Like Cloud Foundry had this idea to have only one base image across all deployments, no matter what. By the day when the log4j vulnerability came out, all the things were operational again within minutes, because they just exchanged that base layer and everything could continue. While other companies were certainly searching and trying to figure out, well, which of my 500 different combinations of operating system and applications that I have does actually have it included or not. So Paketo, as I said, brings in a couple of languages in support mode, and if you happen to have a polyglot environment, then it's certainly useful to consider that idea. Because no matter if you have your Node-based applications, Go, PHP, Java, .NET, or whatever, they will always have the same base image then, and a consistent stack on the bottom. And if something's got to change, it's easily to change all of them. In addition to that, of course, we can see that here now. You have a certain mechanism that builds that image. So if you go back here, and you can see it's very verbose as opposed to a Docker file, so you can very easily trace what's happening. So after the pull was complete, the build pack kind of detected, say, OK, there was no previous image of that type, so I can't use any kind of cache. And these are the things that I found. So it's a Spring Boot application. It uses Tomcat, a couple of other things. So these are all the build packs that came into play to build that image. And then there are some default JVM flags that I didn't specify. So these are the defaults that I could potentially override. And then I see, OK, it's using that JDK. It's using that JRE. It's building all those things. And it also separates, in case of a Java application, again, the things into dependency, various dependency layers, and the class file on top. So with that, you have like a kind of a bill of materials of how your image has been built, what is in there, and that makes it probably easier to handle than the output of a plain Dockerfile. So if you look into images here, we can now see there is that pack version. It's a little bigger because they probably added some things in there that they found meaningful. As opposed to JIB, this also provides the possibility, to do that J-link enabled setting. So if the thing that I showed before, if you want to like pre-package your Java runtime just for the dependencies that you want to have, you can set this parameter to true. By default, it's false. So I can try that real quick and say pack. I should have it in the cache. So with this one, I would say I'm building an image called Java app pack compressed, and I'm setting this environment variable to true. And then it would basically redo the steps from before, but strip down the JRE to a smaller size. So as you can see here, it's also, of course, reusing all the cached layers from before. Just that J-link part hasn't been executed before, so it's doing that now, and then hopefully creating a smaller image in the end. So all right, if I type Docker images now, you can see this one has also been gone down from 318 to 229. Again, this is more than the one the part that I try to squeeze out things on a Dockerfile level. But again, this Dockerfile didn't contain any kind of certificates and other things what the build packs actually put in there as well. However, you have that you can be certain, or you can be sure that the base image and the things that are being put into your image is not something that people just thought of that might be cool. Those build packs, they come out of the Cloud Foundry development, and so they're basically being used there and tested there all the time. So the things that are being used are pretty battle-proof. This is normally the thing. If you rely on another technology, because you know, is it tested well? Is it stable? Is it secure? Is it being used somewhere else? In terms of Paketo, that is. If you look at the other builders in there, you would see there's some from Google, there's some from Heroku. If you don't want to use that Cloud Foundry ones, the Cloud Foundry ones are basically the one you can see here as the Paketo build packs. All right. I'm almost at the end. So if you happen to use not just plain Java, but Spring Boot, you can also use, instead of that pack command, a Maven or Gradle plugin. So if you run Maven, you can specify, I want to build my image using the build packs, and they would automatically do all the rest for you under the hood. Again, that doesn't mean that your code is actually being built inside of the container. That basically means it's being built on wherever you execute Maven or Gradle. But again, the split down, class files, resource files, and dependency jars, I haven't shown you that, but I still can. Docker images. So this is like let's look in the compressed jar, Docker history. And this is 5. Right. So here you see the application slices in here. So this one is basically your application part, and this is the library part. So it's pretty identical. And you can also see that the layers get some kind of updated information of what has been happening there. So that makes it easier for you to track if you just invoke that history command. All right, that brings me to an end. I mean, when I just added this slide because the last time I gave this talk, I got the feedback there is no summary and what should we do now and what is better and what is worse. I mean, in the end, I'm not here to pitch any of these technologies as better or worse. The main intention is, first of all, to make you aware that there is more than a 3 or 4 line Dockerfile, so that you're aware of the options and the possibilities within that options. I mean, for the terms of security and standardization, you can, even if you say, well, I think that JIB idea is good or this buildpack idea is good, but we stick to Dockerfiles, you can still adapt from the things in there and say, okay, this is a lessons learned that they have that I want to use in my own environment. So even if you have various kind of Docker builds, try to make sure you have your base images and as many layers as possible, as consistent as possible. So you can easily figure out if some of them has a vulnerability and you can exchange them. Of course, what I didn't put in there, and this goes without saying, you should always scan your images. But still, if you have very many different combinations, it's more difficult to detect all things. So avoid kind of a wild growth, which is easily possible through Dockerfiles, and automate and standardize as much as possible. And of course, I mean, trying those things out, you have seen it here, it doesn't really take much. I mean, the JIB example, you can just add into your Maven call. For the build packs, you have to install that pack CLI, and then you're good to go. So give those technologies a try. There's probably more out there. So Red Hat has this idea of Source2Image as a part of their OpenShift platform to do a similar thing. As the name says, take the source and bring it into a standardized image. So this idea is kind of spread out into many ways. And I hope we can all learn from that. So again, if you want to play through that, what I have done before, and see the examples live, this is the repo. I try to keep this updated as good as I can. Please forgive me, there are still some Java 17 references in there. I'm going to upgrade it all to 21 fairly soon. But there's no Java 8 and 11 anymore. And with that, I would like to say thanks very much for coming and listening.